and today I'm going to talk about exact matching map recovery in different settings. And all this talk will be based on joint work with Tigran Galestian, Sona Unanyan, and Arshak Dalalian. These are colleagues from Armenia and from France. So let me start with the introduction of the problem. So we will be interested in matching, in finding the matching map between two different data sets. And this problem arises in many real-life applications, and I'll name just a few of them. So first is in computer vision. Imagine a picture of the same object and taken from different angles of different sizes with different luminosity, and we want to match the predefined descriptors of these two images. In another example is a single cell biology, where you have a single cell, you have a set of cells which are encoded using different techniques. So there are two most known techniques, is the sex cell sequencing and another one, I forgot the name. So basically what is happening, we know that there is one cell in the environment, and it's taken, it's sequenced using two different techniques. And the idea is to use these data sets to find which cells correspond to one another. Okay, and another example that could be of interest, especially nowadays with the larger language models and translations and everything becoming very feasible. Imagine two texts, one in English, one in French, one is the translation of the other, and we want to match the words, tokens, or phrases, or maybe like paragraphs, depending on our interests, to see which part corresponds to which one. Okay, and so in this talk, I'm gonna focus on the theoretical properties of this problem and the necessary conditions we need to be able to recover these matching maps. Okay, so going forward, just give you an example what I mean in an application or in computer vision is that we have the same picture of the Sacré-Cœur in Paris, and you can see, for example, in the third picture, the angle is really different than on the one below, and therefore this matching algorithm makes a lot of mistakes. So sometimes this problem can be hard. However, in the first set of pictures, you see that it's quite natural, and the algorithm, it's possible to recover the matching points quite well. Okay, so going forward with the statistical model, we assume to have two sets of random variables, which are x and y, and they are coming from some unknown distribution pi. And we assume that x and x ds, we observe x and we assume that x ds is the shuffled version of distribution y. So we have the same distribution for x and the x ds up to the permutation of elements. Okay, so in other words, we have this relation that xi ds equals to y p star I, where p star is the unknown permutation that we are interested in recovering. Okay, so the goal is to recover this p star from the observations that we have, and we will consider the simplest case of pi, where it's a Gaussian distribution with some shifts theta i's and covariance matrices that are proportional to isotropy to identity covariance matrix up to some variance scales. Okay, and therefore we have this model where xi are coming from Gaussian distribution with mean theta I and variance sigma I square. Whereas for the xids we have the same, but with the permuted mean and variance. And so what we assume here, since xi and xids, they are random noisy observations of the features theta I and theta ids, what we assume is that theta I equals theta ds at point p star I. Okay. Okay, so this is some this I think is the same. So here we will assume, so I already told that we assume that xi I and xi ids are Gaussian IID Gaussian random vectors, and we don't impose any conditions on the feature vectors theta and noise components sigmas. Okay, and we are interested in recovering this pi star. So just to give you kind of an illustrative picture of what is happening, we have our x1 etc xn, and we have our x1 ds etc xm ds, and we have some kind of distances between each other, and we want to find the matching of these two sets. Notice that here the sizes are not the same. So we will start with the size of both equal sizes and n equals m, which is like finding the permutation, and then we will extend it as much as possible in the case where they are of different sizes, and maybe we want to find a matching of much smaller size than the size of smaller set. So there are some possible extensions, but in general the idea is that we have this bipartite graph, and we impose some kind of condition on the distributions of x and the xds, and we want to recover the matching map. Okay. All right, so let me introduce a few quantities that are relevant in this problem. The relevant quantity is the signal to noise ratio, which is defined by the L2 norm between the feature vectors divided by the sigma, the magnitude of noise. Here I assume that sigma is the same for, in the case of homogeneous, that sigmas are all equal. So from the statistical point of view, we are interested in the problem if as how large should this kappa be so that we can recover the underlying matching map exactly. So we are not interested in weak recovery. We don't allow any mistakes. Basically, we want exact recovery of the matching map, and we are interested in the in kappa, how large it could be. So, for example, when kappa is equal to 0, it's impossible because this it's just matching noises which we cannot do reliably. Okay, so. Let me go over some previous work. So in 2016, Collier and Dalalian, they considered this problem of permutation estimation, and they proved that for kappa, when kappa is of order d times log of n in the power 1/4, then it is possible to recover the permutation exactly. So here we have two terms, so d log and just the log to the power square root of the log. I will be mostly referring to the case where d is larger than log n, which is kind of the high dimensional regime, and I will be mentioning this rate over here. So I assume that the first term is the dominating term here. Okay, and the estimator of pi is actually quite simple. What we are trying to do, we minimize the square distances between xi and x pi I ds with respect to pi. So here pi is the, we minimize this where pi is any permutation, but we cannot do this optimization, we cannot solve this optimization problem like directly, but it's a known fact that this is a kind of linear assignment problem, and there exists an algorithm which is Hungarian algorithm due to Knut in late 50s, where he proposed an algorithm for solving the linear assignment problem in complexity of n cube. So actually initially he proposed the algorithm which was n to the power 4, but then it was refined to show that it's actually possible to obtain the complexity of n cube. So actually things are not that bad. In this case it's possible to exactly find the matching map, given that the separation distance is of order d times log n to the power 1/4. Okay. All right.
And below it's impossible. So the optimal part is maybe.
The optimal part. So okay, it's a good remark. So by optimal I mean if kappa is smaller than this, or moreover there exists some kappa that is like equal to this up to some constants, such that it's impossible to recover the pi hat pi star with a constant probability. So actually by optimal I mean that this minimax rate over here is actually optimal, and we cannot improve this rate. Okay. All right. So going forward, we consider the case of rectangular case where we have different number of observations in each set. And the problem is the same, and here we consider also the case when the sigmas, they might be different. Okay, and we will show that this is actually quite important. It can change a lot of things. And yes, so the problem is the same. We have now condition on thetas and also sigmas, because we assume that each point has the same mean and variance, but we are observing its noisy version. Okay. All right. So this is an example illustrating this case, where here we see two pictures where there are 2 points that don't have their corresponding counterparts in the first one. And so even though taking into account these additional points, we want to recover the exact matching map. Okay, the true matching map between these points. Okay, so okay, so here we can write down the general likelihood, the likelihood of our model considered, and I think it might look a bit scary, but it's actually not that scary. So we have the first term corresponds to the likelihood of the xi's that we considered our model, and the second one is for the second set of observations. And actually what we are doing, we are optimizing this function with respect to the constraints theta I equals theta pi star I ds. And it's not difficult to show that after optimizing, we are getting the quantity over here, and something that includes only the variance terms. Okay, so basically, again, what we are trying to do, we are trying to minimize the weighted sum or like normalized sum of distances for a given pi. Okay. And so going forward, we define our estimator lists sum of normalized squares, where we take the minimum over all injective mappings from n to n, and this would be our estimator of pi star. Okay. So a few remarks here. We consider that the variances are known, so actually we can divide by this sum of sigma I squares, and and also what changes compared to the previous one is that now we don't have a permutation, but we have a injection from set 1 to n to 1 to m. Okay, and another slight difference is that now we know that in one of our data sets there are some points that don't have their counterparts, so we call them outliers, and we will measure the distance between inliers and outliers separately. However, we will not impose any kind of condition on the distance between two outliers. If there are two outliers in the same set and they are very close to each other, or like very close to each other, we don't care that much. Okay, so now we will have two separation distances. One is between inliers and one is between inliers and outliers. Okay, all right. So the optimal rate for this case is again the same, up to minor changes from n squared to n times m. And the estimator changes slightly to incorporate these sigmas, which we consider to be known. And again, this problem can be solved efficiently in complexity of n squared m. Typically this is done by adding the smaller set by zeros or like some very large values to complete the matrix, and then we kind of find the permutation in this matrix using the Hungarian algorithm. Okay, so far so good. All right. So yeah, so this is the theorem that formalizes this the result in previous slide, and typically, yeah. So we say that if the minimum distance of these two is larger than the quantity over here, then we recover the underlying matching map pi star with probability 1 minus alpha. Okay, and now the natural question to ask: what if we don't know these variances and we cannot actually divide the distance by, we cannot normalize our distances? What should we do? So actually, if we take a step back to the likelihood function that we optimized with respect to thetas, we recognize that we have also two terms that depend on variances, and in the case where the variances are unknown, we can optimize with respect to these sigmas as well. Again, under the constraint that each sigma has its counterpart in the other set. So here I'm abusing a little bit the notation. One should be careful here because we assume that one set doesn't contain any outliers. So here I assume that I goes from 1 to n, and the pi star I is a mapping to a set 1 to m. Okay? But the idea is clear that we assume that each point has its counterpart in one set, and for those the variances should be equal. So after doing the calculation for for optimizing this likelihood with respect to sigmas, we end up with the following following result. So actually what happens is instead of these sigmas, we put the value of this distance, and it becomes the log, the sum of log of distances. Okay, so this is the estimator for the case that sigmas are unknown. And for this estimator, and in the case where variance is unknown, actually the rate changes. And it changes by having an additional term that is square root of d. So now, in the case where we are in the high dimensional regime, the rate is square root of d instead of d times log n to the power 1/4. And it's, yeah, so the separation distance is of larger order. The estimator is the minimizer of the log of the distances squared. However, the problem itself as an optimization problem doesn't change. You just take the log of xi's, and somehow it becomes kind of more robust and takes into account these effects of sigmas that might be different. Okay, so the complexity doesn't change, and also this is optimal. In what sense? In the sense that we show that if we take into account the estimators, all distance-based M estimators, namely in the definition we take the distance between xi and x pi I, and we put any function rho I that is non-decreasing, and we take into account all possible estimators that can be obtained using this procedure of putting whatever rho comes to mind, like Huber, or like anything that might sound robust or like makes sense to use. And over this set of estimators, we show that there exists a setting where the separation distance is as large as square root of d divided by 5, and any estimator from this set capital M fails to detect pi star with constant probability. Okay, and so this is the formulation, or the exact formulation of the theorem that shows that this rate is actually minimax optimal, and also the same holds for any estimator. So even if we do not take into account all distance-based estimators, but something completely different that might be not based on the distances, then if kappa is larger than d log n to the power 1/4, then again it's impossible to detect pi star with the constant probability. Okay, so okay, so another question that is okay, let me comment a bit on the results on the lower bounds that we obtained, and actually in lower bounds what we played a lot were the sigmas, where the covariance the covariances, and in that case we kind of make a case where the sigmas they grow exponentially large, and then it becomes impossible to detect these matching maps. And so what gave us another idea that let let us fix the maximum over sigmas and assume this rho r sigma is something finite that doesn't grow very. So it doesn't go to infinity or to infinity. Okay, then we were able in this case to separate these two distances. What I mean is that given that this quantity is finite, then we are able to determine two different separation distances for inliers and between inlier and outliers, such that these the recovery of pi star is exactly possible. Okay, so here we have for the inliers we have the same rate as before in the problem of permutation matching, and for inliers and outliers we have the square root of d times r sigma term, and the rest is the same. Okay. And in this case also, where we consider the mildly varying variances, a similar lower bound is also true, and we can show that if both of these are if the inlier distance is of order of d to the power 1/4 and the outlier is square root of d, then any estimator fails to detect pi star with probability 1/4, say. Okay, so here I would like to kind of show the summary of what was done. So in the case where the sigmas are known or are equal, so this boils down to the same rate. So if the sigmas are known, we use the normalized least squares. If they are not known but equal, so we use just the least squares, and these are basically the same estimator. And we show that the optimal rate is d log n to the power 1/4. However, when we introduce the outliers in one of the data set, we need to incorporate these two distances, but the rate doesn't change. So we again have d log n times m to the power 1/4. However, when sigmas are unknown, the problem changes a bit, and in case of permutation estimation, this rate still remains to be true, and it's achieved by least sum of logarithms, which was obtained by optimizing the likelihood function with respect to sigmas as well. However, for the cases where we have outliers in one of the sets, the separation distances are becoming different. Okay, so in the case where the ratio of sigmas is finite, we were able to separate these two separation distances. However, in the case of arbitrary sigmas, we get a rate which is larger than in the case of without outliers. Okay, so this means that the problem becomes a bit more, slightly more difficult when you have two sets and you don't want to match all the points. So you have some kind of outliers in your problem. Okay, so how much time do I have? 15? Good. So now we have seen the cases where we are trying to find the permutation, and also when we have one of the sets containing outliers. Now let's go even further and assume that we have two sets of Gaussian. Again, the model stays the same. We have the same assumptions on what we had previously, but now we are trying to find a subset of n, which is of cardinality k star. so the assumption is now that there is a matching of size k star, which can be formulated as an existence of an injective mapping from S star, from a subset of 1 to n to m. And we also require this equality of thetas on this subset S star. So now the problem becomes even more harder because we don't know the size of we might not know the size of the matching, and now we have like exponentially many subsets to try to look at and to find the matching for them. Okay, so we define a set of all k matching maps such that this set is a subset of n. It has a cardinality k, and pi is an injection between the set S and the set 1 from set from 1 to m. Okay, and the procedure here would be very similar to the ones that we have seen, with slightest changes that we take now the argmin over all pi's that represent a k matching, and also we have to take into account that by changing our pi, the support of this mapping also changes, and we don't want to incorporate two wrong points into adding into our loss function. That's why here it's not I from 1 to n, but it's the support of the pi considered here. Okay, so the first result that we show is assume we know, so we don't know k star, but assume we somehow know that the k that we have chosen is smaller than k star. So for example, we're trying to match the key points of two pictures. We can always take k equals 1, because thinking that 1 point should be at least matchable, but assume that we know that, like, I don't know, 50 of them at least have their matching points. So this result shows that given that the separation distance kappa all is large enough, which is the same quantity as we have seen before, then what we are actually doing, we are recovering a subset of the true matching S star. So basically we are doing a support recovery on S star, but now we don't know exactly the value of k star. So if it happens that we chose k to be strictly smaller than the k star, then this should be a subset of size k of S star, which is of size k star. So what we are doing, we are actually recovering some subset of S star, and we are sure that on this subset the value, our estimator coincides with the true pi star, So basically we are recovering a subset of our true matching map, and yes, so this is kind of important, because if we don't know the true value of k star, and we don't want to estimate it or whatever, if we are sure that we are having a k strictly smaller, then we can be sure that the matching that we will end up with will be a subset of the true matching. So this is the meaning of this result. Okay, but now imagine that we don't know k star, and we actually want to estimate k star. What we are doing, we are actually solving this problem. We are solving this problem for all values, not all, but for some values of k, and we are looking at the cost function that we have here, that we are optimizing, and we are kind of looking into the increment of this cost function after adding another point, another pair. Okay, so if after some point this difference becomes large, this difference phi hat k plus 1 minus phi hat k becomes very large, which is larger than something of order d, then we say that these 2 points, they are not true pair, they are outliers, and we stop there. So we are increasing the value of k star until something like this happens. So we start with k equals 1, and then we add another point, and then we see that increment is not that large, etc., 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 until the increment becomes really large. And for this procedure of estimation of k star, we actually proved that the probability of k star being equal to k hat, and using this k hat solving the LSS problem will result us into recovering the true matching map pi star. Okay, and yes, so this is the general. So here I think, okay, so here there is something unknown, which is sigma 0 square, which is the sigmas, but here I assume they are known, so it's all right. Okay, so in general, when the variances are unknown and also k is unknown, so now we have two set of parameters that are unknown and kind of they depend on each other as well. No, they actually don't depend that much. But here we can refine this estimator obtained here using the estimator for sigma 0 square instead of its true value. So what happens is that here is the general algorithm for finding the triplet k hat, the sigma, and the matching map pi hat. Okay, so we start with k, which is k mean, which is the value that we know that should be present in the matchings, and we compute phi hat k and phi hat k plus 1, and we are iterating until we reach k equals n, or this distance becomes large. And if not, and then we output our triplet k hat, sigma, and pi. Okay, and we prove that in this procedure, when we don't know any variance and k star, for appropriate choice of these tuning parameters lambda and gamma, we are able to recover the true matching map pi star with probability at least 1 minus alpha, and with the same separation distance as before. Okay, so to sum up the results of this part is that we show that the optimal rate for this problem is again d log n to the power 1/4, and we solve this problem using the k LSS estimator, which is given here, and it can be done even when k star is unknown. So we design a method, that data-driven model selection algorithm that adaptively chooses k, and for that chosen k, we have that the solution of this problem pi hat LSS k hat equals to pi star with high probability. Okay, and now the question is, how do we solve this problem, because now this problem becomes even more complicated since we need to choose a subset of size k from n, which we have exponentially many of them, and we cannot do it like choosing a subset and then using the Hungarian algorithm to solve it. But however, there is a nice trick in the literature which is known as minimum cost flow problem, which actually provides a feasible solution, and with complexity that is up to some minor things hidden here. It's square root of k star times n square. And let me briefly give the idea of the minimum cost flow problem. So we had our bipartite graph of our high dimensional observations and the distances between them. Okay, so we had n plus m vertices and n times m nodes. Now what we are doing, we are adding two more vertices. One will be called source and one will be called sink. We add all the connected edges from source to the first set and all the edges from the second set to sink. And we set the cost of transferring from source to the first set all the orange edges. The cost of passing flow from them is equal to 0. However, and also we put constraints on capacity of each orange edge. So we want it to be from 0 to 1. So the capacity of passing through each orange edge is 1. The cost of it is always 0, because we don't want to penalize anything that is connected to source. We want to penalize the rest, which is connected between x and xds. What we are doing, we are trying to put a flow of size k in the hope that eventually the solution of this flow problem, where from source it comes the capacity of k, of water flow of capacity k, and then it passes through each edge by at most one capacity 1 for each edge, and then it needs to come to sink with capacity k. And so we hope that it will end up, we don't hope, it's kind of, if it solves, then it will find the best way, the minimum cost way of this flow passing through this x and x ds. Okay, and finally, to give you a bit more mathematical formulation of this minimum cost flow problem and why it can be solved efficiently, is to notice that it is actually a linear program, and we have our dig, which are the distances between our observations, and we try to minimize this sum with respect to w's, where w's are ideally 0 or 1, but we relax it to be a real number from 0 to 1. And we put some conditions on these wi's. So the condition that corresponds to finding, to having a matching of size k is that the sum of all weights should be equal to k. And also these two conditions on the sum of weights, such that so for each xi we are trying to match exactly 1 point, and that is incorporated in this constraint. And also for each pair in the second set we want it to be matched to 1 point in the first set. Okay, and yeah, unfortunately, I don't have time for numerical experiments, but I'll stop here. Thank you very much.
I'm sorry, I may have asked the same question earlier, but anyway, so can you do this by, or why can't you do this by testing? If you know the variances.
If you know the variances, no problem. You can do the testing. You will get same results, I believe. Okay. The separation distance would be.
Yeah, the separation distance for pairwise testing.
Yeah, I think so. Yeah.
And if you don't, it's because
if you don't know the variances,
in the last case you said so, because the variance are the same for every I, right? It's just 1 sigma and sigma.
So here. Yes. Yes. Here. Yes. So here it's also possible to do with sigma I and sigma j. But it's so it's
no. I mean, if you know a minimum k-mean and you say, okay, so for the k-mean I just map the closest pairs.
Yes.
And I use this to estimate sigma, and then I do testing.
Yes. I think it's also possible to do like this.
But won't it be like more efficient than the flow matching, the flow minimum flow stuff?
So the problem I think with this might be that when you are matching first k mean points, you are kind of being very greedy, right? But here it's kind of more not greedy, like a more smarter algorithm. Maybe the difference could be this, but in terms of efficiency, I agree that if you take the smallest distances, match them, it's super fast. And the minimum cost flow is a bit more, has higher complexity. Yeah. Yes.
Yes. So here you have some identity in terms of covariance of the noise, and I think that many things break down if you start to have unknown covariance. Have you think about it?
Yes. Actually, yeah, it's a very good question. So the question is, what if we don't have identity here and we erase these sigmas but put a general covariance metric sigma here? So actually the things do break down in some sense, and what especially breaks down is it's becoming from linear assignment problem to being a quadratic assignment problem, which is known to be NP hard, NP complete. Yes. So it's the kind of considered as the hardest problem between NP problems, and we cannot solve it efficiently. But in the case, so I can partially answer to this question, saying if we have sigma, which is unknown, but is the same for both cases. So we say that there is a general covariance matrix here and here. Then I think it's possible to do. And so the optimization of this maximum likelihood with respect to this covariance matrix sigma will give us the sample covariance matrix, and what we would like to actually do is to minimize the log det of log determinant of this sample covariance matrix with respect to this permutations pi. And this is not NP complete. This can be solved using an SDP solver. So it's an SDP optimization problem. But if we have two different ones, So I think there are some room for playing with them. Yeah, but in general, it's a quadratic assignment problem that is NP hard. I don't know if I answered
what we discussed.
Okay.
Just a little question, which I'm not sure I understood. In your lower, you have two lower bounds, one
yes.
for distant base, where the root d is present, and another one for all, where there is no root d. And
yeah.
If I understood it right. Do you understand what's going on? Yes. So, yes, this one.
So here is this. Yeah. So this is by the construction, which actually forces these distances to be square root of d, but the estimator is like m estimator. But here, so I don't know what's going on that much here, because it's the Fano lemma and
no, but what I mean, do we believe that here in the second, do we believe that there is an estimator that would achieve this d to the 1 force overall, or okay?
Yeah, I don't know, but so typically what happens that these rates obtained for lower bounds, they might have a slight gap between the minimax optimal that you have, but if it's possible to have an estimator, no, actually it's not possible, because here we prove this is a particular class. But yeah, okay, so if it's possible to find an estimator in general that achieves this rate instead of square root of d, I don't know.